So now back at the lecture guide, you can either watch those videos if you like to understand that simulator and pause it and restart it and rewatch it, or you can go here through this little page that shows you the details of how to use that simulator if you want to read about it, or do both. You are going to have lots of practice here with using that simulator though. All right, part F then says, generally describe what we mean by a chance model and what it is showing. Anytime you're asked to describe your simulation or your chance model or asked to do a simulation, you need to make sure you do a screenshot. So I did a screenshot of my simulated screen and then I put it here and dumped it right into my solutions. My screenshot shows what I entered in the applet and also shows the actual chance model over here on the right. And I've just written a little bit about what we're looking at here. So I said a chance model is also called a distribution of sample statistics. Remember, each of those dots is a sample statistic we would expect to get. So it's showing us the expected usual statistics we'd get if the parameter were equal to the value you entered as the hypothesized value. In our case, we entered a parameter of 1/6. 0.16667. So if that's truly the value of the parameter, these are the statistics we expect to get if we do a sample of size 60. The distribution will be centered at the value you hypothesized for the parameter, and it was centered around 0.16667. Notice it came out a little bit different than that in the mean. It's because it's a simulation. But all of you who do this on your own simulation on the computer will get something very close to 0.1667. So all the statistics you see, all the dots you see will be close to the value of the parameter, with about half of them being higher than that and about half of them being lower than that. So about half the dots are more than 1/6 and about half the dots are less than 1/6. We create this chance model so we can see the amount of spread, amount of variation that we should expect from the sample statistics. This is telling me the variation and spread, the types of statistics I should expect to get. So what does each dot represent? Each dot represents the number of times that it rolled a 5 out of 60 total rolls. Each person who recreates this simulation on the computer is going to get a slightly different chance model. But when they have the proportion of successes button selected, then we know that they will have a mean of approximately 1/6 or 0.166667. If the die is fair, what types of sample statistics would be normal, usual, and expected? So your answer to this right now, when I ask you guys this in Module 1, I'm just asking for you to give me an estimate based on your chance model. I'm going to personally say, it looks to me like it would be normal, usual, and expected to get things like 5 5s out of 60, or 6, or 7, or 8, or 9, or 10, or 11, or 12, or 13, 14, 15, 16. So for me, my chance model had quite a few dots that came out 5 rolls out of 60, 16 rolls out of 60, but I'm not comfortable saying that 17 times you'd get that, or 3 or 4. That doesn't seem plausible, right? That hardly happened at all. When they did this 100 times, only once did they get this few, only 3 5s out of 60 rolls. So the ones that have a lot of dots above them are like 5 rolls out of 60, 6 rolls out of 60, all the way up to like 15, 16. Yours might look a little different, but it should be pretty close to what I'm saying. So I said it would be plausible when rolling the dice 60 times to get between 5 5s and 16 5s. So here up to here. Getting 4 5s or less, or getting 17 5s or more seems very unlikely. Again, because getting 17 or more didn't happen. It only happened once or 0 times. Getting 4 5s or less only happened once or happened 0 times. So those seem like unlikely things to happen. So overall, what would our conclusion about the research question be? Our research question was, is this die fair? Is this die rolling 5s a sixth of the time in the long run? So notice then, our chance model shows that if the die is fair and we roll the die 60 times, then we should get between 5 5s and 16 5s. That was the normal, usual, expected sort of statistics to get. Our observed statistic from our sample was 14 5s out of 60. Our p-hat was 14 out of 60. That's what we actually observed at the beginning of the problem. So our observed statistic is a normal, usual, expected sort of statistic to get if the die is fair. It fell in that range of being between 5 and 16. So I conclude it's plausible that this die is fair.